Hello, and welcome to our Chapter 7, Sections 1 through 3 video on sampling distributions. We are covering 3 sections today because each of the sections are kind of short, and we're also only going to focus on the things that are really important in these sections. So when we talk about sampling distributions, first, before we can define that, we have a couple other vocabulary words that we want to talk about first. So the first one is a statistic. So I know you take the statistics class, but a statistic versus statistics is kind of different. So statistics is just the overall, how do we gather data, how do we analyze the data, and all that whole science. A statistic, singular, is really a number that describes a sample. So specifically, if I were to say 75% of high schoolers really like to use social media or something. So that 75%, because it's talking about high schoolers in general, does not count as a statistic. But if I said I took a sample of high schoolers and found that 65% of them really like to watch SpongeBob, that 65% coming from a sample would be a statistic. When it's not from a sample, then it's called a parameter. So, easiest way to remember this is that a statistic comes from a sample, a parameter comes from a population. It's also nice because a statistic starts with S, sample starts with S, so that's easy to remember. Parameter starts with P, population starts with P. So that's how I remember it. So let's do an example. Identify the population parameters, sample, and statistic in this situation. So turkeys need to be roasted to a safe internal temperature of 165 degrees Fahrenheit. For my first time roasting a turkey, I use a meat thermometer to measure the temperature of the turkey at 4 randomly chosen locations. The minimum reading I get is 170 degrees Fahrenheit. So first, let's just start by identifying the population and sample. We've done this before in the past when we first learned what a population and sample was. But here, in this case, because I'm trying to roast a turkey and I'm checking randomly chosen locations on this turkey to get my temperatures, then the sample would be the 4 randomly chosen locations. So if the sample is the 4 randomly chosen locations, then the population would have to be all the locations, because population is always something about all. Okay, so now that we have the population and sample stated, let's move on to the parameter and statistic. So for the parameter, this is supposed to be a number that describes the whole population. So if we read back to the problem, we have 2 numbers. We have the 165 number and the 170 number. So our parameter needs to be a number that describes the whole population, which we said was all possible locations on the turkey. Versus the sample, for our statistic, the number has to describe the 4 randomly chosen locations. So rereading our problem, it says out of the 4 randomly chosen locations, the minimum reading she gets is 170. So that comes from the numbers from my 4 randomly chosen locations, so that's from my sample. So that would be considered my statistic, which means the 165, it's talking about the whole part of the turkey. You need your whole turkey to be cooked all the way. So 165 is talking about all possible locations of the turkey, so that would be our parameter. Okay, so now that we can tell the difference between population and sample, parameter and statistic, now let's talk about what a sampling distribution actually is. So here's its formal definition. A sampling distribution is the distribution of values taken by the statistic in all possible samples of the same size in the population. So I know that definition, it's a formal definition, didn't make a whole lot of sense. If we were to explain it, it takes up a lot more words than that. So basically what we're saying here is, remember, a distribution of values is if we were to make a graph of some sort, we would be able to have a distribution or a data set. But then we are looking at samples of the same size. So imagine we were choosing at West Broward, a random sample of 20 students. So each of my samples that I take are going to be 20 students large. And when we talk about all possible samples, I'm basically trying to look at, in all of West Broward, all the different combinations of 20 students that I can get. So that would be all possible samples of the same size. There's a bajillion ways I can do this, but that's how many we want to talk about when we talk about all possible samples of the same size. There has to be a lot of them. But within each of those samples, we're going to measure something. So in my example here, at West Broward, I'm curious about like people's heights. So out of each sample of 20 students, I'm going to measure their heights and then calculate the average height in that sample. So then I'm going to do this again by picking another sample of 20 students, measure their heights, figure out the average in that sample. So I should be getting different averages each time I take a sample though, because each of my samples are probably slightly different from each other. So the average is going to come out slightly different each time. But if I take all the averages and then make a dot plot with all of them, it could look something like this. So right now this graph isn't a graph of people's heights. It's a graph of people's, like, samples' average heights. That's what a sampling distribution is. So we're looking at lots of different averages at a time. So the reason why we want to do this is because with a sampling distribution, it's actually a much better describer of your population. Because you're dealing with lots of different samples, and each sample's averages or proportions, whatever you're like measuring, it's a lot better representation of your population. So in this example, we were talking about averages, but for this next section, I'm going to focus on population proportions. So remember, proportions is like a fraction or a percent of some sort. So if in a population I'm measuring actually, like, rather than like people's average heights or whatever, if I was measuring what percent of people generally watch SpongeBob, then I can pick a sample of 20 students at West Broward, ask them, do you watch SpongeBob? Figure out what percent of those 20 students watch SpongeBob, and then plot that one dot. And then I could go on, find another sample of 20 students, ask them if they watch SpongeBob, figure out what percent of them watch SpongeBob. That would be another dot. And do this a bajillion more times with all the different possible combinations of 20 students. Once I've made that graph, that sampling distribution of proportions, then I can look at it and see what shape it is, where the center is, what the variability or like how spread out it is. So when we talk about the shape of a sampling distribution, the shape always matches the original population. So if your original population, if all the averages or the proportions were skewed to one side, then your shape of the sampling distribution is also going to be skewed to one side. Unless there is a stipulation. If our n times p, like n standing for the sample size, p standing for the population proportion, if you multiply them and you get a number greater than 10, and n times 1 minus p is also greater than 10, if both of these things apply, then the shape is approximately normal, even if the original shape of the population was not normal to begin with. So remember, normal is what we like because we want that like bell-shaped curve. If we're talking about the center of the sampling distribution, so like the middle of the graph basically, the center always matches whatever the population proportion was. So if I knew that like overall all West Broward students, the percent of them that watch SpongeBob is 60%, then 60% is also going to be the mean of the sampling distribution. Because remember, your sampling distribution is not a graph about like each individual student at school, it's about the proportions of each sample. So the center of that is going to match the population proportion, but the spread of it is not going to match. We actually have a formula to calculate the new standard deviation. So variability is how spread out something is, our data set is. Standard deviation is how we measure that. So the formula to calculate that is big square root of p times 1 minus p divided by n. So this formula helps us calculate the standard deviation of a sampling distribution. Once I calculate this number, what it means is if I were to take samples of whatever size I had, whatever my sample size was, the sample proportion, the percent that I get from the sample, will typically differ or typically vary from the population proportion by whatever that number is. So it's kind of like that, like average distance from the mean kind of meaning, because it is a standard deviation. Just here we're talking about proportions instead, so it's like the amount that you would typically be different from the true proportion or the true percentage. Okay, so let's do this with an example. Suppose that 35% of all first-year university students attend school within 50 miles of their home. A polling organization asks a simple random sample of 1,500 first-year university students how far away their home is. Let p hat be the sample proportion, so that's our symbol for the sample proportion, who live within 50 miles of their home. So first we're going to calculate and interpret the mean of the sampling distribution of p hat. So when we calculate the mean of the sampling distribution, we just said the mean of the sampling distribution has to match the population proportion. So it has to match whatever percentage that our population is. In this problem it says 35% of all first-year students attend school within 50 miles of their home. So that's our population proportion then. So our mean is going to be 35% as well. We're just going to turn it into a decimal because that's how we do math. So 0.35 is our mean. For our interpretation, in samples of size 1500, because that's our sample size, the mean of sample proportions is 0.35. Nothing too crazy. So now let's calculate and interpret the standard deviation of the sampling distribution. So standard deviation, I'm going to plug in into the formula that we had from up here. So p for us was 0.35. 1 minus p, 1 minus 0.35, divided by our sample size, which was 1,500 in this problem, because it said we had a simple random sample of 1,500 first-year university students. So doing those calculations out, we get 0.0123. So that's our standard deviation. Interpreting that, kind of following along our definition here, in samples of size 1,500 instead of size n, the sample proportion of the students who live within 50 miles of their home, because that's what this problem was about, typically varies from the population proportion by 1.23%, because the decimal that we got, if we turned it into a percentage, would be 1.23%. So that's what we're basically saying. For even though the true population proportion of students who live within 50 miles of their home is 35%, if we were to look at the spread of our sampling distribution, it would vary by about 1.23%. Okay, so then our next part, we're going to try to find the probability that the simple random sample of 1,500 students will give a result within 2% of the true value. In order to calculate this probability, we need normal curves first. So in order to check if it's actually normal, then we can check n times p and n times 1 minus p. In this case, n is our 1,500 number, p is our 0.35. So then doing that and the 1,500 times 1 minus p, we get 525 for our first number, 975 for our second number. Both of them are clearly bigger than 10, so this is going to be a normal curve problem. So with our normal curve problem, I can draw out my normal curve. I'm going to label the mean and the standard deviation that I calculated from before, so the 0.35 and the 0.0123. So the probability we're looking for is a result within 2% of the true value. So our true value here is the 0.35. So within 2% means we're looking at 2% on each side of our middle number. So within 2% would be 33% and 37%. That's on the left and right of the 35%. So that's the probability we're looking for right in the middle here. And because we're dealing with normal curves, that means we're finding two z-scores and subtracting the percentages from each of the z-scores. When I plug into my z-score formula, I have the 0.33, that's the value that I want, minus the mean of 0.35, divided by my standard deviation of 0.0123. When I do that, I get negative 1.63. I'm going to do the same thing for my other number, and I get positive 1.63. So now I'm looking for those two z-scores in my z-score table. So negative 1.63 will give me 0.0516. Positive 1.63 will give me 0.9484. So subtracting the bigger percentage minus the smaller percentage, I get 0.8968. So that's my probability for this one. Last example, find the probability that the sample proportion would be greater than 38.5%. So now we already know it's a normal curve to find the probability. So we just need to draw our new normal curve, find our new z-score, calculate the percentage. So here's my new picture. I have the mean of 0.35. I'm looking for greater than 0.385. My standard deviation is still the same as before, the 0.0123. We find a new z-score. I end up with a z-score of 2.85. So looking at my z-score table, I'm looking for positive 2.85. So 2.85. 5 would be here, 0.9978. But because I'm shaded to the right, that means I have to do the 1 minus whatever percentage I got, so it would be 1 minus 0.9978. So my final answer for my probability is going to be 0.0022, or 0.22% is my probability. All right, that's it for this section. Thanks for watching. Bye.